Let's look at a technique of integration called integration by parts. This is a really useful technique to integrate products of functions. We begin with the product rule and we integrate it. So much like we integrated the chain rule to find how to integrate using substitution, now we integrate the product rule to find a formula for integration by parts. The integral of the derivative of the product of two functions is just going to be the product of the functions by the fundamental theorem of calculus. Now if I differentiate that product and expand out the integrals, I can see that this is the integral of f times the derivative of g plus the integral of derivative of f times g. Let me now rearrange this for the integral of f times, so this is equal to, so the integral of this product f times the derivative of g is equal to f times g minus the integral of g times the derivative of f. That's a bit of a mouthful when written out in this explicit functional form. Let's use a simplifying notation. Let u equal f of x and v equal g of x, so that du equals f prime of x dx, dv equals g prime of x dx. The formula we just found can be written as u dv is uv minus the integral of v du. And I've just ignored the constant for now. Once a final integral is done, one can add in the constant of integration. This is known as the integration by parts formula. It's not clear at all at the moment why this might be useful, but it turns out it is. Let's try a couple of examples to see how this works. So this is a classic example, the integral of x times the cosine of x. So it's not clear why integration by parts is going to work here, but we do have the product to do function. So let's have a go at trying this. What we need to do is select u and v, and we want to select u and v where we're going to differentiate one and integrate the other, such that the resulting integral at the end of the process becomes simpler than what we started with. Let me let u equal x, so that du is just dx, and let dv equal cos x dx. So I'm after turning this integral x cos x dx into u dv. So if I identify u equals x, dv equals cos x dx, v is sin x. So therefore, the integral becomes u times v minus the integral of v du, which is sin x dx. So what's happened here is by using the integration by parts formula, I've turned a product into an integral that I can now calculate. So this becomes x sin x plus cos x. And after the last integration is done, we add in a constant. Okay, let's try a couple more examples to see how this works in a bit more detail. Let's look at x to the n times log x. We need to select a u and a dv such that we differentiate the u and we integrate the dv in order to come up with something simpler at the end. Now clearly the integral of the log here is the difficult part. So what we choose is that the logarithm we know how to differentiate, x to the n we know how to integrate. Let's put a table off to the left here. Let's let u equal log x, so that du is 1 over x dx, and then let dv equal x to the n dx, so that v is x to the n plus 1 over n plus 1. And note when we do this integration here for v, we don't bother with a constant of integration. It's worth exploring why we don't need to do that. So let's now use these formulas for our integral to simplify it using the parts formula. It becomes u times v minus the integral of v du, which is x to the n. So integrating and gathering everything together, I have, and we add on our constant of integration. An intriguing thing to note here is that this also works for n equals 0, even if there was no x in there. So if I had integrated this with n equals 0, I would just have a 1 in here, and that's another useful trick for integration by parts. Let's try another example. Let's try the integral of cot minus 1x arc cot of x. Now at first sight it doesn't look like by parts is useful at all here, but with reference to the previous example, which would have worked when there was only one function log x, we can also apply the same trick here by imagining there's a number 1 in here. So let's try that. So we know how to differentiate cot to minus 1, so we let that equal u. du, and we let dv equal just dx, so that v is x. And now what's going to happen here is when I use the integration by parts formula, I've got u times v, x times cot minus 1x, minus the integral of v du. So that's x over 1 plus x squared, and the minus becomes plus. This second integral I can do using substitution, and that works out to be a half log 1 plus x squared. And we can use a substitution there because x is the derivative of 1 plus x squared. In those previous examples, one of the functions was chosen to be differentiated and the other integrated, with the result that after using the by parts formula, we wound up with a simpler thing to integrate. In fact, we can use integration by parts even when this isn't the case. Consider this example, e to the x sine x. If I choose e to the x or sine x to integrate or differentiate, I'm not going to wind up with anything simpler at the end of the day. I'm just going to jump between e to the x and sine or cosine of x. But let's try integration by parts and see what happens. So let's try, for sake of argument, u equals e to the x, du is e to the x dx, dv is sine x dx, so that v is minus cos x. This gives me, so using the integration by parts formula, I seem to have got no further forward because e to the x cos x is just as difficult to integrate as e to the x sine x. Let's, for sake of argument, do integration by parts again on this second integral. So I carry my minus e to the x cos x to begin with. Then I'll do integration by parts for the second time. Again, I'll let u equals e to the x. Then what we've got on integrating by parts for the second time, on this second integral here, using these formulas, minus e to the x cos x from my first integration by parts, then plus e to the x sine x from my second u times v. Then we're left with the integral of e to the x sine x dx. So I seem to have got no further forward because I seem to be back where I started. However, note this minus sign here. That means that I can take this integral and move it across to this side of the equation to give me the integral of e to the x sine x is a half e to the x sine x minus e to the x cos x. So that's an antiderivative of the function e to the x sine x, so I can add in a constant for the set of all of them. We can also use integration by parts to derive what are called reduction formula, where an integral that can be quite complicated can be reduced in its complexity by using integration by parts. Here's an example. If I want to integrate cos to the n of x dx, then one can derive a reduction formula to reduce the integral in its power to a similar integral but with a lower power. And we can do this using integration by parts. Let me write this as I subscript n. And let's begin as follows. It's not immediately obvious how to go about this. So what I'm going to do is I'm going to write my integral as cos to the n minus 1 times cos x. And then let's go through integration by parts. Okay, so let's let u and v be defined in this way. Then I can write. So again, this seems to be no further forward because I end up with an integral which looks just as complicated. However, I've got a sine squared in there, and using the identity that sine squared is 1 minus cos squared, what I get is the following. Or, written in terms of I subscript n, where I've taken this part across to the left-hand side, and dividing through by n gives me the result.